This video covers momentum. Our topic of momentum is actually very similar to what it was last year. So momentum is a quantity of motion resulting from an object's inertia. Remember that inertia is an object's resistance to changes in motion. And momentum has to do with velocity. The greater an object's momentum, the more difficult it is to stop. So remember that momentum will be represented by a P, and it is mass times velocity. Now, because we have velocity involved, our momentum is actually a vector quantity, that it has both magnitude and direction. So the direction of our momentum will be in the same direction as an object's velocity. So here, the velocity's direction is going to be really important. Now, the units for momentum will simply be kilograms, which are the units of mass, times meters per second, which are the units for velocity. Another important concept deals with our change in momentum. Before we can look at that, let's look at an old equation. The sum of the forces is equal to mass times acceleration. Remember that acceleration is simply the derivative of velocity with respect to time. So if we take our change in velocity out and put in our mass, well then this is momentum. So our change in momentum with respect to time also gives us our net force. So this equation is one way that you might see it on your equation sheet. Another way is if we multiply each side by our change in time, and then we can take the integral of a force function with respect to time, and that will also give us our change in momentum. Now, change in momentum is also known as impulse, which is represented by a J. So you basically have two equations for impulse, one with an integral, one without. Now, the first equation you want to use when you have a force that varies with time, meaning that you have a function of force. The second one you want to use with constant or average forces. But depending on the information that you have, this can actually be used as three different equations. So down here at the bottom, you have one equation if you are given for force and time and you're asked for impulse. The second equation is if you're given a mass and velocity and you're asked to solve for impulse. Again, a change in momentum. Now the third one is probably the most useful. You can find a relationship between force, time, and change in momentum, or impulse. Now remember that momentum is a vector, meaning that if it's moving in some arbitrary direction, it can have three different components. Normally we've seen two up until now. So if you're asked for your momentum in the x direction, it is simply the velocity in the x direction times your mass. The momentum in the y direction would be the velocity in the y direction times your mass. And the same thing for the z direction, which is coming out of the page. Now, if you're asked for our resultant, it would be the square root of the momentum in the x direction squared plus the momentum in the y direction squared plus the momentum in the z direction squared. So just like last year, whenever two or more particles in an isolated system interact, the total momentum of the system remains constant, meaning that the momentum at the beginning is equal to the momentum at the end. So if you have two objects interacting, which in this equation I only show two objects interacting, I simply have the momentum of the first object at the beginning plus the momentum of the second object at the beginning should all be equal to the momentum of the first object at the end plus the momentum of the second object at the end. Now, again, remember that momentum is a vector, meaning that if we are talking about the other two dimensions, that we can say all of the momentum in the x direction will be conserved, all of the momentum in the y direction will be conserved, and all the momentum in the z direction will also be conserved. So, if there is no momentum at the beginning in those directions, there will not be any momentum at the end in those directions. Now, our law of conservation of momentum is normally seen with collisions. So, our definition of a collision is an event during which two particles come close to each other and interact by means of forces. Now, this doesn't mean it has to be a physical contact. It just means that the forces that these two objects exert on each other are enough to create an interaction. Also, the time interval during which the velocity changes from its initial to final values is assumed to be short. The interaction force is assumed to be much greater than any external forces present. That means if we apply a force on an object and it causes a change in velocity, that means that that force is much greater than all other forces present, meaning we can pretty much disregard normal force and force of gravity or any other forces that are interacting that are not causing this change in momentum. Now, the two main types of collisions are elastic collision and inelastic collisions. Now, for elastic collisions, you do want to think of bouncing or elasticity, but it doesn't always have to be that situation. Now, the most important thing is that for elastic collisions, momentum and kinetic energy are conserved. So we saw this property last year, but we didn't really use it very often. This year, we're going to use it a lot more. Also, for inelastic collisions, kinetic energy is not conserved, and that's a huge, huge idea that we're going to, again, see a lot more of this year. In either case, momentum is conserved. So again, it doesn't matter the type of collision, momentum is still being conserved. It's just that in inelastic collisions, kinetic energy is not conserved. So again, in inelastic collisions, we have two subtypes. We have perfectly inelastic collisions, which is going to be the most common, and simply inelastic. Now, the difference between the two is for perfectly inelastic collisions, these objects will stick together. What that means is that the velocity that one object has is going to be the same as the velocity of the second object. So our equation will look like it does down here at the bottom, that the velocity is shared by both masses. In simply inelastic collisions, when colliding objects do not stick together, some kinetic energy is lost. Like in a case where you have a ball that's bouncing off a floor, even though it's bouncing away from the floor, it might seem like an elastic collision, but kinetic energy would not be conserved. And a problem would normally tell you that. Again, for elastic collisions, both momentum and kinetic energy is conserved. Again, the most common situation is when you have two objects coming toward each other and then they bounce away perfectly away from each other. Again, what this means is that our momentum at the beginning is going to be equal to our momentum at the end. And then another property that's also going to be very helpful is that our kinetic energy at the beginning is equal to our kinetic energy at the end.